Due to the lengthiness of the first part of section 3.6, I have decided to cut that video off at 20 minutes and tack on the rest here in part 2. The problems do get a little bit lengthier, so it's good to have a little bit more time to talk about them. We have another theorem. The book calls it something a little bit different than what I'm calling it. I've seen it called this in other textbooks. It's called the complex conjugate theorem. I believe our book calls it the conjugate zeros theorem. But either way, it basically says that if a plus bi is a root of a polynomial, so is a minus bi. It will always happen that way. Imaginary roots will always come in complex pairs. Always, 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 always. You cannot have one imaginary root without its complex conjugate also being a root. Alright, we're going to do another problem where we talk about knowing the zeros of a polynomial, but needing to find the equation of the polynomial. So I want to find a polynomial p of x of degree 3 that has integer coefficients and zeros at 1/2 and 3 minus I. First of all, the complex conjugates theorem says that if you know that 3 minus I is a root, 3 plus I must also be a root. So now I know my 3 roots of my third degree polynomial. Now I'm going to go put that into my complete factorization. So x minus the first root, x minus the second root, x minus the third root. Now I'm going to have to do some major multiplying here in order to get this to be nice. There are a couple ways of going about doing this. Probably the most direct way of going about doing this that'll make the most sense is to go and write this and multiply these two polynomials together and leave the x minus 1/2 till the end. Now, one of the ways that I've seen some of you using, instead of using the little arrows for distribution, I've seen some of you guys go and try to use the box. I think that is an excellent idea. You would have x, negative 3, and I on one side of the box, x, negative 3, and negative I on the other side, and then you would find the area of every box. X squared, negative 3x, xi. Negative 3x, 9, negative 3i. Negative xi, 3i, negative I squared. One of the things you're going to notice happens is that these are opposites, these are opposites. This becomes 1, because I squared is negative 1, so negative I squared must be positive 1. So you're left with x squared minus 6x plus 10. And look, imaginary components gone. Now I can go and re-multiply the x minus 1/2. Now, for those of you who have me before, even some of you who've been paying attention earlier in the year, I hate fractional exponents, or fractional numbers and roots. So one of the things I tell my students they can do is this. If you have a fractional root, just take the denominator, stick it in front of the x. Now I can go back and I can do this again. You can either use the arrows to multiply this out, or you can use the box, which I think is a not bad way of doing this. So I'm going to put 2x and negative 1 on this side of the box. X squared, negative 6x, and 10 over here. And now I'm going to find the area of all the boxes. 2x cubed, negative x squared. Negative 12x squared, 6x. 20x, negative 10. And then here are your like terms. So the final polynomial p of x is 2x to the third minus 13x squared plus 26x minus 10. It is the polynomial whose roots are 1/2, 3 minus I, and 3 plus I. The book does this problem in a little bit different fashion. I think you'll find that my way is easier to understand based off of your prior knowledge. We've seen that a polynomial factors completely into linear factors if we use the complex numbers. If we don't use the complex numbers, we factor it over the real numbers. You can't always simplify everything into a linear factor. Remember, a linear factor means that in the factor you have an x to the first. If you don't use the complex numbers, then a polynomial with real coefficients can always be factored into linear and quadratic factors. So when you have a quadratic factor left over, under the real number system, we say that it's irreducible. But it's only irreducible over the real numbers. If you can factor it, if you're given permission to factor it over the complex numbers, then it's not irreducible. So let's let p of x equal x to the fourth plus 2x squared minus 8. And I want to start this problem off by factoring p into linear and irreducible quadratic factors with real coefficients. In other words, we're going to factor this under the real number system. Now, if you look back up at this problem, I feel like I've seen one of these before. This is one of those quartic functions that's in a quadratic form. So if I pretend like it's quadratic, if you factor it by finding the two numbers that multiply to give you 8, but add to give you 2, you find out that it's x minus 4, x plus 2. But it's not really a quadratic equation, it's a quartic equation. So all I have to do to account for that is this. Then x squared minus 4, that's a difference of 2 squares, which does factor over the real number system. Look at that. Oh, I've got it backwards. You got to stop me in the middle of a video when I've got it backwards. Let's try that again. This should be positive and that should be negative because I want a positive 2 in the middle. Sorry about that. All right. X squared plus 4 cannot be factored under the real number system, but x squared minus 2 factors into x plus the square root of 2, x minus the square root of 2. Now, I'm going to go back and I'm going to factor it completely into linear factors with complex coefficients. All right, so we're going to take the answer from the previous part. And now we're going to talk about factoring this, which was irreducible. Well, because it's the sum of 2 squares, it factors into x plus 2i, x minus 2i, and then the other two factors remain. So now this has been factored completely into all linear factors with complex coefficients. And that concludes complex zeros in the fundamental theorem of algebra.